Hi guys. Today we're going to start talking about air pressure. I'm actually going to break this up into a lot of different topics. So we're going to just start really simple and just talk about atmospheric pressure and what changes atmospheric pressure. So we'll start with the idea of what is air pressure? What is air all about? So if you think about air, most of the time you don't really recognize the fact that it has mass and it takes up space. So if you take like an empty water bottle and you put the cap on and you try to crush it with your hands, you're not going to be able to do that because there's air inside taking up space, which is going to push back against you. And you only notice that when you have an empty container like that. Now, if you take the cap off the container and try to crush it, obviously you're going to be able to do so because all the air gets forced out. So the idea is air pressure is caused by the force of those molecules bouncing around off of surfaces. Now, if you think about all the air above your head right now, it's quite a bit, right? It goes up for several miles above your head. And we talked about all the layers of the atmosphere. So, air actually gives off a pressure which we can measure in different values. And we're going to take a look at some of those values later on. But one value that is a measurement of air pressure is called PSI. And you may have heard of that before. That just stands for pounds per square inch. Now, if you're at sea level, you're at the ocean and you're standing on the beach, above your head, there's a lot of air. And every square inch of that air essentially gives off 14.7 pounds. So that's 14.7 pounds of air above your head in that square inch. Okay. Now, obviously, if you spread that out over a large area, more square inches, that's more pressure. It's a lot of weight. And we can demonstrate that really, really in a cool way with this demonstration of putting an egg into a bottle. Or what I'm going to do is I'm going to show you how to put a water balloon into a bottle. So I'm going to do that demonstration right here. This is a demonstration of air pressure. As you can see in front of you, there is an empty jar and there is a water balloon on top of it. Now, if I push on the water balloon, that's not going in there. Okay, but what I can do is I can take the air outside and force it into the jar by changing the pressure inside. So what I'm going to do is I'm going to heat the air up inside by burning some paper. Take that off momentarily. I'll put it back on in a second. I'm going to light this paper on fire and I'm going to stick it inside of the jar. Okay, and then I'm going to put this on top and watch what happens. Ta-da! There we go. So I just force that into the jar by changing the pressure inside of the jar. No. Okay, so how in the world did that all work? Let me explain a little bit of the science behind that. I said it was caused by a change in pressure. So what's going on there? Well, this picture shows you a bottle with an egg on top, and you can do this with a hard-boiled egg if you want to. That's kind of fun. Or you can just do it with a water balloon. So what you do is you take a match, you light it on fire, or you light some paper on fire, you put it into the bottle. And when you put this egg or water balloon on top, you're blocking off the air, right? So now all the air inside is heating up and heating up, and those molecules of air are getting faster and faster and faster, and they're escaping out of the bottle. And if you watch that demonstration really closely, you probably saw the water balloon like kind of jiggle around and hop around on top of the bottle. That's all the air inside that's escaping out of there. So it's all forcing its way out. And essentially what we create is a partial vacuum inside of here. So the air pressure inside of here has dropped a lot. The temperature went up, but the pressure dropped. Okay. And because there's less pressure in here, there's a lot of air out here that's like, hey, we got to balance that out. So all the air outside is now forcing and pushing on the water balloon or on the egg, and it pushes the egg or the water balloon right into the bottle to balance out that pressure. And now that the balloon is now inside, everybody's happy, and it just stays inside of there. Okay, so that's the science behind that. It's all due to changes in temperature, which causes a change in the pressure inside of the bottle. And all this air outside of here is strong enough because remember, it's 14.7 pounds per square inch. It's strong enough to force this in any direction. You could turn this bottle upside down and do it upside down if you wanted to. It works both ways. The pressure outside is caused by those air molecules moving around. Okay, now Next slide is an important one. There are a lot of different factors which can change the pressure. One factor which we already talked about, and we'll take a look at this on the next slide, is altitude, right? The higher up you go, the less air there is, the less pressure there is. That makes sense. Temperature is another factor which is going to cause a difference in pressure, and that is demonstrated by that water balloon into the bottle trick. Okay, humidity is another one that you don't often think about, but that changes pressure as well. Now, what is actually going on here? Really, what it boils down to is a difference in density. If I change the temperature, I'm changing the density of the air molecules. And if I change the density of the air molecules, then I'm changing the pressure. Okay, less molecules per volume means less pressure. Remember, it's all the bouncing of those air molecules off the surfaces which is causing pressure. If I have less of them, then it's less dense, then it's less pressure. So if you look over here, this is important. This idea that density and pressure are directly related to each other. Okay, so if I have a denser material, then it has more pressure. Denser air, more pressure. Now, what actually changes the density and what actually changes the pressure? These factors over here. So this is temperature. If I decrease the temperature, it gets colder. Well, now everything's slowing down. The molecules are coming closer together. They're contracting. They're getting more dense, therefore more pressure. Colder air has a higher pressure. Okay, and warmer air has a lower pressure. And that's what you saw with the demonstration of the water balloon into the bottle, right? It got really hot inside, the pressure decreased, and all the air outside was trying to force its way in. Altitude. If you go down in altitude, if you go down to sea level, then there's more air, it's more concentrated, it's more dense, then there's more pressure. Now, if you go up in altitude, let's say you go to the top of Mount Everest, now there's less air, it's less dense, it's less packed together, it's more spread out. That means there's less pressure. Okay, so they're opposites. Humidity, and this is what we're going to look at in the next upcoming slide. If you have a less humid air, it's more dry air, it's actually got a higher density, and therefore it's got a higher pressure. And it's actually related to the atomic weight of the molecules, and we'll look at that in a second. If you have more humid air, then it's less dense and it has less pressure. Okay, and that's a weird one, but we'll look at that in a second. Okay, now with that in mind, let's go on to some of these individual concepts here. So altitude, we already talked about this chart in your reference table, right? The higher up you go, the less atmospheric pressure there is, and that's because there's less air up there, right? And less air molecules means less pressure, less dense. Okay, and if you go down to sea level, it's really a lot of air above your head, and therefore it's more pressure. Okay, so hopefully that makes sense to you. That's a pretty simple concept. Now, temperature. We kind of looked at this with the water balloon. If you have warm air, warmer air is less dense. It spreads out more, and because it spreads out more, it expands, it's less dense, it's going to rise, right? Because it has less pressure. Now, once it gets up to a higher altitude, it's going to cool off, and as it cools off, it's going to become more dense because all those molecules are coming back together, and now it sinks back down again. And so we have this convection of air due to temperature differences. And that convection of air causes wind. Okay, it's all due to differences in temperature, which are caused by differences in density, which are caused by differences in pressure. Okay, they're all related to each other. So this is convection. We've talked about that a lot. And temperature changes the pressure. Okay, now the last factor was humidity, and this is a really weird one. So let me explain this as best I can to you. So if you replace gas molecules with heavier molecules, then the density of that gas will decrease. Okay, so this is kind of weird. So what I'm doing is I'm taking water vapor and I'm putting it. Imagine you have a jar. Okay, and in that jar you have air, and I'm going to take some of that air out of there and replace it with water vapor. Okay, now if you think about the average composition of air is made out of mostly nitrogen and some oxygen, mostly. Okay, So the average composition of air has a weight of what we call 28 AMU, atomic mass units. You'll look at this in a second. If I replace that with water, water vapor has a mass of 18 AMU. So I'm replacing the heavier air with lighter water molecules, and therefore it's becoming less dense. It's less heavy, less mass. Okay? So what that basically means is really hot and humid air, like maybe down south, hot humid air has a lower pressure, and colder, drier air has a higher pressure. Now let's think about that demonstration, right? So we had the container. This is a little container of air, and inside of there, it's mostly nitrogen, right? Most of the air, it's like 78% nitrogen. Okay, so we'll just say nitrogen molecules. Each one of those nitrogen molecules has a mass, remember, molecules are really two nitrogens. So if you look at the periodic table, nitrogen has a mass of 14. If you have two of them, that's a mass of 28. Now, if I take all of these molecules here, there are a total of 30 of them, you can count them up, and multiply that by 28, the total mass of this container of air molecules is 840 atomic mass units. Okay, so that's dry air, no water in it. Now, if I want to put water into it, I'm going to replace some of these nitrogen molecules with water molecules. And water molecules, remember, water is H2O. That's two hydrogens, so a mass of 1 times 2, that's 2, plus a mass of 16 for oxygen. So that's a total mass for a water molecule of 18 AMU. So this water molecule has a lower mass than a nitrogen molecule. So I'm putting less mass into this, okay? And if I add it all up, and you can look at the math down here, there's 24 nitrogen molecules and 6 water molecules in here. Total it all up, it's going to come to 780. So the total mass of this is less than the total mass of this. Water molecules, lower mass, air molecules, more mass. So by making it more humid, adding more water to this, it actually becomes a lower density and therefore has a higher pressure. Okay, so that's kind of interesting to think about. All right, now I'm going to just show this to you. We can measure pressure on a map uh, across the globe or across the United States, and we can measure pressure in different values. All right, and I showed you pounds per square inch before. We don't typically use that for meteorology. What we use are millibars, and you can see all these numbers that are plotted all over this thing. If this was just numbers, it would be super ugly, but they colored it. Okay, now if you look over here, this area has a higher pressure. Why? Well, due to differences in temperature and differences in humidity and differences in partially altitude, but mostly differences in temperature are going to cause this. Okay, so this has a high pressure area over here, and there's a low pressure area over here. Now, what we can do is we can draw lines. These are called isobars, bar for barometric pressure, and these lines are connecting places of equal pressure, and we can make what's called an isobaric map. And from that, we can actually see these lines on here. It's exactly like a contour map, which we were looking at earlier in the year. Now, here's the big thing. These lines, in some places, are really close together. Okay, and where those lines are close together, it's kind of like the lines close together on a topographic map, right? If they're close together, it's really steep. There's a big change here in pressure. And because there's a big change in pressure there, that's going to indicate that the air is going to try to get from here, where it's high pressure, to where it's low pressure. Kind of like going back to this idea in our water balloon demonstration, right? There's a higher pressure out here and a lower pressure inside of here, and it's trying to rush from high pressure and push its way into the jar. The balloon's in the way, or the egg's in the way, and it forces its way in there really quickly. Okay, so going back to the map, if you think about the map here, we have a really high pressure area over here in the United States, and we have a really low pressure over here. All the air is rushing away from the high and trying to get to the low. Okay, and that's an important concept. So the idea is where the isobars or iso lines are really close together, that's where it's super windy. Okay, and when you think about a windy day, it's due to this idea of differences in pressure And if there's a lot of lines close together, if it's a big change in pressure coming, that means we have windy conditions, and typically stormy too. Okay. Well, we're going to look at all the direction of these lines and all that stuff later on, but I just wanted to at least demonstrate that to you. You might see this like on the weather report. Here's the high, here's the low, the big bold letters H and L, and you have a big strong pressure gradient, which just basically means it's super windy conditions. Okay. So those are the factors that affect pressure. Remember, altitude and temperature and humidity, those three factors really factor into what this pressure is all about, whether it's high or whether it's low. And we're going to look at high and low pressure individually on our next lesson. Okay, that's it.